Chapter 7 is on gravitation. In the first part of the chapter, it's talking about a bunch of these first beginner astronomers, scientists, and how they study comets, moon, the sun, the other planets, and how they move through the Earth's sky, through the Earth's sky at night. And one of the first ones that we see, or if you read the chapter, is on Tycho Brahe. And he didn't use any telescopes for his instrumentation. He actually just he constructed these huge pieces of equipment to measure the time period of the planets as they moved across and with comets and everything like that. And one of his assistants was Kepler. And with the instruments from Tycho and with what Kepler studied on his own, he came up with a couple different laws that we still use today. The first one of Kepler's law says that paths of planets are ellipses with the sun at one focus. So if you kind of remember, and if I marked right here, ellipses have two foci. So if we look at an ellipse, oh, come on, pen. Excuse me. Sorry about that. All right, so here's an ellipse. And these 2 points right here, those would be the foci, or the focuses. Okay. Now, Kepler's second law says that an imaginary line from the sun to a planet sweeps out equal areas in equal time intervals. Now, Kepler found that the planets move faster when they are closer to the sun and move slower when they are farther away from the sun. He also found out that there's a mathematical relationship between the periods of the planets and their mean distances away from the sun. And that's where we get into Kepler's third law. And Kepler's third law says that the square of the ratio of the periods of any two planets revolving about the sun is equal to the cube of the ratio of their average distances from the sun. Or in other sense, if we look at the formula, time A planet over time B planet, and that would be squared, so that ratio would be squared, is equal to the radius of planet A over the radius of planet B, or the ratio of radius of planet A over the radius of planet B is cubed. So let's kind of look at an example of Kepler's third law. Let me move this up a little bit. Move it out. Okay, so Galileo measured the orbital sizes of Jupiter's moons using the diameter of Jupiter as a unit of measure. He found that Io, the closest moon of Jupiter, had a period of 1.8 days and was 4.2 units from the center of Jupiter. So the period of 1.8 days is how long it took to orbit around Jupiter. Callisto, the fourth moon from Jupiter, had a period of 16.7 days. Using the same units that Galileo used to predict closest distance from Jupiter. All right, so formula, T of A over T of B squared is equal to R of A over R of B cubed. So let's use A as Io and B as Callisto. And let's put in our information for there. So if Io is A, its period is 1.8 days. And the period for Callisto is 16.7 days. Squared is equal to, now the radius for Io, as given to us, is 4.2 units over x. And that would be cubed. So we need to figure out what x is. Okay, so a couple different ways that we can possibly do this. One way is we can go ahead and square our ratio on the left-hand side. So if I take 1.8 divided by 16.7 and I square that, I come up with 0.0116, and that would be equal to 4.2 units over x, and that would be cubed. So then what we need to do is get x by itself. So I would have to multiply both sides by x and divide by 0.016, so x cubed equal to 4.2 units cubed over 0.0116. Okay, so x cubed would be equal to, take 4.2 to the third, or cube it, divide by 0.0116. So x cubed, I'm coming up with 6,386.90 units. Now to find what the radius is, we have to take the cube root of 6,386.90 units, and actually that would be cubic units. Alright. So 6,386.90. I'm coming up with 18.6 units. Okay, so does that kind of go along with it? Well, since Callisto is the fourth moon out from Jupiter, so its radius should be a whole lot bigger than Io's. Now, let's kind of put 18.6 back into our formula and let's see what we come up with. That's another way that we can do this. So if we take 4.2 divided by 18.6 and we cube that, I'm coming up with 0.0115. Now, when we squared our ratio of the time period, it came up with 0.0116. 0.00116, 0.0115, that's pretty close. So I would consider that, yes, that is the correct answer. Now let's look at another example. This one says, an asteroid revolves around the sun with a mean orbital radius twice that of Earth's. Predict the period of the asteroid in Earth years. All right, so we're still using the same formula. TA over TB, and that would be squared, is equal to RV over RB, and that would be cubed. So let's have A represent the asteroid, and B, that would represent Earth. So we're trying to find the period of the asteroid, so we're trying to find T of A. I'm just going to put that as X. Now, T of B for Earth is just 1 year. Squared is equal to, now it says that the asteroid revolves around the sun with mean orbital radius twice that of Earth's. So if we put 2 times Earth, that would be over Earth, that would be cubed. So let's kind of clean this up a little bit. Over on the left-hand side, we still have x over 1 year squared, and that is equal to, now, since we have Earth on both the numerator and denominator, we can take that out, and we have 2 cubed, which that would be equal to 8. So x over 1 year squared is equal to 8. X squared is equal to 8 years, or 8 years squared. X would equal to the square root of 8 years squared. And 8, or square root of 8, turns out to be 2.8 years. Okay, now along with Kepler, we have Newton again, and Newton had a law of universal gravitation, and he found out that the magnitude of the force on a planet due to the sun varies inversely with the square of the distance r between the centers of the planet and the sun. And with that, he came up with gravitational force. Now, the gravitational force is a force attraction between two objects, must be proportional to the objects' masses. And with that, he came up with the law of universal gravitation, which the law of universal gravitation is just dealing with attraction. Objects attract other objects with a force that is proportional to the product of their masses and inversely proportional to the square of the distances between them. What in the world does that mean? Force is equal to, now G, this is the universal gravitational constant, 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared. So that's G. Now M1 and M2, those are our two masses, over the radius or the distance between them squared. Now another thing is we can also find out how long it would take for a planet to orbit around the sun if we use this formula. Time is equal to 2 pi times the square root of r cubed, which is the orbital radius around the sun for that planet, over g, our universal gravitational constant, times the mass of the sun. Now what I'm going to do is I'm going to photocopy a table for you to help you with some of these problems that has the mean distance and the masses of the different planets and of the sun here in our solar system. So this should help you out with the first assignment. If you have any questions, please let me know, and thank you for watching.